Hi everyone, thanks for coming. We're very happy to have David Victor here today. This is maybe the fullest I have seen this room, by the way, in quite a while, so that's a very positive sign.
Or the temperature's going down.
Yeah, that could be. But in any case, I think we're all very excited to have you here. I'm not going to give you a lengthy introduction. You certainly publish stuff occasionally, so that's good.
Publish and perish, and
Yes,
still alive.
yes. So we'll just let you get started. Thank you.
Thank you. Thank you. Well, I'm David Victor. I'm a political scientist, and I'm going to give you a talk today that is partly about political science, partly about atmospheric chemistry in the Arctic. And it's narrowly around questions of soot and methane, black carbon and methane in the Arctic region. But I'm going to try and suggest to you along the way that this is actually a talk about how to begin to get serious about the climate change problem. Because anyone who's been following this, who's not been living in an undisclosed location for the last 30 years, knows that this is a really, really hard problem. The fundamental problem is created by carbon dioxide, mainly from burning fossil fuels. Deep decarbonization is expensive. Deep decarbonization, 80–100% reductions in emissions. Carbon dioxide is a long-lived pollutant in the atmosphere, which means that you spend a lot of money today for benefits that appear only far in the future, and because it's globally mixed, those benefits accrue mainly to other countries. So structurally, the problem almost guarantees that it's impossible to solve, and the last 30 years of diplomacy seem to be evidence in that direction. Maybe things are changing around the Paris Agreement. And so a lot of political scientists and some public international lawyers have been thinking over the last couple decades and intensively over the last 5 years around how you could change the cooperation problem from a seemingly impossible problem involving very large numbers of countries with different interests, some of whom actually want the agreements to fail, to a problem that's easier to solve by working in smaller groups. In clubs, if you like. And there's an interesting long literature about club cooperation and the appropriability of those benefits and so on. I'll talk a little bit about that in the course of my remarks today. There's also an interesting literature that has emerged in parallel, some in the atmospheric science community, some now dragged into the foreign policy community, thanks to some articles by me and others in Foreign Affairs and a variety of other places, to make the case that if you looked at short-lived pollutants instead of long-lived pollutants, that the political economy might be more benign. In part because short-lived pollutants are short, and their atmospheric lifetimes is shorter. And so if you've got a politician who's got not a long time horizon, shall we say, and some of them perhaps shorter than they think, that the way they discount benefits from activities that have high near-term costs means that they're not going to focus a lot on carbon dioxide, but they might focus on other pollutants where the benefits are more tangible and more apparent. So that's the kind of underlying political logic that has brought the parts of the atmospheric science, climate science community, and political science community together into some research programs around this question. But it's easy to say that, and a lot of us have now said that. The real question is, numerically, what are the benefits? Which are the countries that matter? Just going from a large group of countries, 180 countries at these negotiations, which those who have been to them know they're just a complete circus, to a small group of countries doesn't guarantee success. You have to think about the geometry of the club. Who's in the room, who's not in the room, what are the incentives for them to do things, and so on. I think that is now the cusp of the interesting social science research in this area, and I want to present to you a paper, or a draft paper that's under review in Nature Climate Change about this issue, around thinking about the actual incentives and the geometry of the clubs in the focus of this. I am going to focus on the Arctic. I'll talk a little bit more about that. For those who are not climate scientists, just a little bit of radiative forcing here. The Earth every day, on average, gets hundreds of watts per square meter averaged around the planet's surface from the sun. Imagine hundreds, but we don't have incandescent bulbs anymore, but imagine back in the Stone Age when we had incandescent bulbs, a 300 watt or so light bulb over a 1 square meter surface. That's kind of the quantity of energy coming in from the sun. A lot of it reflected back immediately from bright surfaces, clouds and ice and so on. The rest of it absorbed, radiated back and forth inside the atmosphere, and then eventually radiated black body back out from the top of the atmosphere. The climate change phenomenon is created by a small imbalance So you're talking about hundreds of watts per square meter that are coming in and out of the planetary system, and then a tiny imbalance measured in single watts per square meter that is what's causing the climate change problem. There's a tremendous amount of leverage in the system. A lot of people are excited about that leverage for geoengineering reasons and so on, something I'm quite heavily involved with, but I won't say anything more about that. Let me give you some numbers to give you a sense of what the number about the relative importance of these different pollutants. So if you have 3 years of your life and nothing better to do, you can join the IPCC. You get involved in making charts like this. I just spent 3 years on it, and so I'm not signing up for the next one, but I did write a large part of the last one. So this is from the last IPCC report. This is neutral. These are changes in the net radiative forcing in the planet since 1750, with some confidence intervals around this and so on for the different major greenhouse gases. So here's carbon dioxide. Here's the villain in our story for the long term. The change in radiative forcing is on the order of 1.5 watts per square meter. What's interesting to a political scientist is that carbon dioxide is not the only problem. And so we have different gases with different physical properties that generate different politics, and that's what to me is very interesting about this here. We have a variety of industrial gases and ozone. We have nitrous oxide, another long-lived gas. We have down here an area where I've been doing a lot of work, which is black carbon, which is the main warming agent. It's soot. Soot is tricky because it you co-emit black carbon along with organic carbon. And so in the atmosphere you have cooling and warming effects, and I'll disentangle that for you in a little bit. But here's what I want you to focus on, which is on the order of 1.5, 1 3/4 watts per square meter is coming from carbon dioxide already as measured in the atmosphere. And from the short-lived warming pollutants, from methane and from soot, you have total, and some industrial gases that are short-lived, you have total radiative imbalance that's almost at the same scale. And so in theory, at least, with a significant amount of, with significant reductions in these short-lived pollutants, you could see a change in the net radiative balance in the atmosphere that would appear relatively quickly. So that's the kind of basic logic behind the problem or the opportunity here. I'm going to focus today on the Arctic. The Arctic is zonally isolated or partially isolated from the rest of the planet. That is interesting to us politically because it means that pollutants that end up in the Arctic region disproportionately affect other countries in the Arctic region, and of course the Arctic region is more sensitive to overall changes in atmospheric warming. So if there's any region on the planet where the countries might be more motivated to do something about the climate problem, you might expect to see it in the Arctic region. Of course, in the Arctic region you have countries whose interests vary. You have countries, I spent a lot of time in Norway. The Norwegians are clean and green and mean, and they're a fighting machine about doing things about the climate change problem, to such a degree that they've already kind of largely cleaned up their own economies. So the game in Norway is trying to figure out how other countries, the Russian interests may be a little bit different, those who study Russia. And so you have countries with different interests, but you have potentially a highly concentrated motivation to do something about the problem because it's going to appear there first, and because the pollutants tend to stay in the Arctic region. So I'm not saying that the analysis I'm presenting here today is going to solve the whole climate change problem. What I'm saying is that if we can do the math in the Arctic region and understand the interests and incentives for countries to cooperate there, that we can begin to do that in other parts of the world. I'm going to show you some analysis today that suggests that actually the incentives to cooperate in the Arctic region are intense, but the geometry of cooperation is very, very different from the way we thought about the problem originally. One more footnote here, which is for political scientists who study international relations, one of the things that's very interesting about the Arctic is there are existing institutions that are effective, and in particular the Arctic Council. So essentially all Arctic nations are members of the Arctic Council. There's like a little kids table that has China and India at it, so not really little kids, but they have separate participation rules in the Arctic Council. And that's interesting to us as political scientists because it means that you have existing institutions in place that could get countries together to cooperate about the problem. One of the hardest things to do in international cooperation is even when there's a blindingly obvious incentive for countries to work together, the larger the number of countries that need to work together, the harder it is, in part because the transaction costs of getting all those countries together, those transaction costs are very high, and if you have existing institutions that are effective, they can help reduce the transaction costs. That's the kind of logic and awful lot of international relations scholarship that looks at institutions, looks at that logic and looks at the question of whether and how institutions actually help reduce transaction costs. So this all looks auspicious for cooperation in the Arctic region. In order to calculate the actual incentives for countries to do something about the problem, we need to work through 3 steps. We need to know something about the emissions that are causing harm in the Arctic. And I'm going to look at harms associated with impacts on human health, impacts on crops, which turn out to be actually not that important, and impacts on the climate. We need to know something about the source-receptor relationships. So it's one thing to do a globally averaged analysis and show the planet as a whole has an incentive to do something about global warming or an incentive to do something about particular kinds of pollutants. But it turns out that no decisions are taken at the planetary level because there's no czar, despite what people think about the black helicopters of the UN and so on. There's no czar. And so what I'm going to try and do is change the unit of analysis here and focus in on the incentives at the country level. Individual countries, what are their incentives to do something about the problem, and to what degree can they realize the benefits of those actions themselves? Because an activity where the benefits flow back to the individual country that takes that action, that's going to be much more likely than one that requires lots of different countries to cooperate. And then you need to know something about the concentration impact relationship for each of these different pollutants, by which I mean in different language. If you put soot into the atmosphere, you need to know something about the concentrations of soot that eventually end up in the ambient air in different parts of the Arctic region, and then the effect of those concentrations on things that people care about. Human life, the productivity of crops, climate warming, and so on. So those are the 3 steps I'm going to walk you through. I'm going to give you a sense of the intuition behind the analysis. I'm going to periodically drill down a little bit to just show you the nuts and bolts of the analysis, and then I'm going to try and stay up at a kind of higher level, maybe 10,000 feet, 15,000 feet, rather than at sea level at the entire for the entire talk. Okay. There's a series of papers that report this. There's now a lot of papers that are reporting this. This paper is the one that was an ambitious idea. It was revised last week, so it was revised in October. This is the paper that I'm going to be talking about today. This paper does the first reports on, for which I'm an author, the first reports on the 3-dimensional climate chemistry modeling in the Arctic. This is the TM5 model that you'll see more about this, and then these are 2 papers from an international relations scholar at Princeton and me that try to work through the incentives for different countries to do something about the climate warming problem. I will say, for those of you who are political scientists, we are still very early days in getting the discipline to be serious about the problem of climate change. And partly that's because most of the work in the discipline is not framed in a way that you can work on climate and people in the discipline see that you're doing something that's actually political science. And so part of my surreptitious, not really surreptitious, my mission here is to show how we can work on serious political science questions, but embedded in climate science. But it has to be done in teams. And so I'm talking about a paper that's got 4 authors on it from a bunch of different disciplines, and this is just the only way I think you can operate in this domain. Okay, first, what do we know about emissions and control costs by sector and by country? This is an area where there's been a lot of work over the last 7 to 8 years, partly because the United Nations Environment Program and several research groups, including at GASA in Austria, have invested in building massive databases and begun to start to characterize at least some of the uncertainties. And let me show you a couple slides, give you a sense of what that looks like. This slide shows you, without the headline, so that's problematic, but this slide shows you for black carbon on the top and for methane on the bottom, millions of tons of emissions, shows you current, and this is current 2005, but as those of you who work with these models know, even the very best energy models are running only with 2015 data. So there's actually a huge base year calibration problem in many of these models, and the more esoteric your model, the bigger the base year calibration problem. We're still working with 2005 as a base year, and if people are looking for something important to do in this field, here's one thing you can work on. And then these are projections out to the year 2030, using a standard, what are called business as usual projection. This is a projection in which you assume that policies don't really change from what countries have in place right now. The economy grows, the population grows. The population growth is very easy to predict. Economic growth turns out to be harder to predict, but actually relatively easy compared to most of the other things. And then you look at what the emissions might actually be from that. I will say that almost every single model that does business as usual projections for almost every pollutant that we're interested in around the climate change problem is hot, meaning that the projections, the business as usual projections are all high. And I think that's because the modeling community, which is dominated by a kind of operations research style work, knows very, very little about how societies kind of normally put new policies into place and so on. And so if one were to develop some new algorithms and ways of thinking about the kind of autonomous development of policy, it would result in radically better baseline projections. And so these projections, I think, are hot compared to what, meaning they're overstatements as to what's likely to happen in the absence of additional policies. But it gives you a sense by different regions of the world, because most of this work has been organized geographically by region, not by country. One of the innovations in the work that I'm presenting here today is that we're going to look at the country level of resolution and not at the region. And that's because essentially all international politics is done by country governments and not by regions. So it's really important to look at the country level. And we know something about different sectors: agriculture, waste, industrial processes, and so on. This is dominated by an agriculture story in methane and fossil fuel production, including natural gas production. And in soot, it's dominated by agriculture, in particular burning of biomass and power plants. So those are the kind of dominant sectors. We have continued to collect data at the sectoral level. I'm not going to do anything more with it in this talk, but one of the next papers we're going to work on is do the cost-benefit calculations by sector. Why is that interesting? Because if you're a student of political economy, many policies, in fact, I would say all policies that are adopted at the national level are not adopted by nations just thinking about their own global national interests. They're adopted by nations where different sectors have different political strength. And so we now have the capacity to quantify some of that at the sectoral level, and we can build a kind of political economy model, if you like, that's operating at the sectoral level inside countries. But you have to walk before you run, and so today I'm just going to present the analysis at the country level. So we know actually quite a lot about emissions, and we think something about how to project those emissions by sector out into the future. The community thinks it knows a lot about what it costs to control emissions, and so there's a big database sitting behind this of the costs of all the different emission controls, and we think we know something about the uncertainty with which those different emission control efforts actually have an impact on radiative forcing, what we ultimately care about. Climate impacts. So let me give you some sense of where I think we know something and some sense of where I think we actually are deluding ourselves and we know less than we think, but give you a sense of kind of where the science is headed in this area. So what I'm going to show here is on the left for methane and on the right black carbon. So I used soot in the very beginning of the talk. I'm going to zero in when I'm talking about warming on just on the black carbon effects because of the co-emitted problem of organic carbon. We'll look at the data in just a second. And these are Monte Carlo analyses of the impact of different kinds of policy measures on the impact of those emission sources on radiative forcing. Let me put this into context. Here are a bunch of different policy measures that could be taken to affect power plants and the emissions that come from power plants. Those have very wide tails, and this is some representation of the underlying uncertainty about the effect of power plant changes in technology, for example, putting baghouses, scrubbers to a lesser degree because of the pollutant involved here, but baghouses and precipitators in particular, on power plants, and then the impact of all that on the overall, the net radiative forcing effect of the emissions that are coming off the power plants. And actually the community right now believes that overall the effect of those measures is to cause a net cooling. Why is that? Because black carbon is co-emitted with organic carbon, and because the technologies that reduce that also have an impact on sulfur, and sulfur is a precursor to sulfate, and sulfate is a very large cooling agent and so on. So actually, kind of one of the ironies in the kind of autonomous desulfurization of the world's energy system that's going on right now aggressively in China, although there's a range of views as to how much is really happening on the ground, one of the effects of that is to actually increase the radiative forcing, that radiative forcing on the planet right now. So I'm not saying that we should dump more sulfur into the lower atmosphere. There are a lot of reasons to desulfurize, but that there's a mask coming off on the warming effect. It's actually 0.3 of a watt, maybe 0.4 of a watt per square meter. Really, really big number. So what's interesting in looking at this is if you just focus on the black carbon on the right-hand side here, we think we know something about the underlying uncertainty about the impact of power plant measures on black carbon and then therefore net radiative forcing effects. But what's really disturbing to me is if you look at these improved cook stove programs, they're all right over here and the tails almost don't exist. We believe that we actually know a tremendous amount about the impact of improved cook stove programs on radiative forcing. The overall effect, almost all the studies suggest the overall effect is to lessen warming. So you improve the cook stoves, usually by raising the combustion temperature, normally by forcing more air into the combustion chamber. That causes less black carbon. That in turn causes less warming as a result of the cook stoves and so on. But the literature, the actual test results in the field show that, the variation in results is massive. This is an area, if you're interested in this question, an area for tremendous technical advance very soon is to characterize, which I think can be done almost completely with the existing literature, and some expert elicitations would be to better characterize the underlying uncertainty around the impact of these different measures. So we're beginning in our own work to do an actual uncertainty analysis. I'm only going to present median results today. We're churning out on a daily basis the uncertainty analysis around this. We can only do indicative uncertainty analysis, and we can't do Monte Carlo kind of analysis because we don't know what the shapes of the distributions are for the underlying variables, and so we don't know how to run the Monte Carlo analysis. This is a big, big blind spot in the literature, and so to the extent that you're compelled to work on soot and methane and other short-lived pollutants, I think possibly the single greatest area of scientific advance is to understand the underlying uncertainty around these control measures. Okay, that gives you the kind of flavor of what's in this work around emissions and control costs, what we know, what we are pretending we know, and we actually have no clue about. I want to talk a little bit about how we do the source-receptor relationship for each pollutant. This is a really complex atmospheric modeling problem. We're just going to show you a couple slides to give you a flavor of how this is done, because there's a right way to do it, but it's computationally hard to impossible for the form that I'm going to present here. And so there's a reduced form way that actually looks like it works really well. And so I'll give you a sense of what people are doing in this area. The right way to do it, this is from the Sand et al. Paper that I mentioned earlier, Nature Climate Change, at the beginning of last year, is to run a four-dimensional model of physical transport and atmospheric chemistry in the Arctic region. And through that, then, and you know something about the emissions that are going into the atmosphere, you can then figure out the fraction of emissions that end up in the Arctic. And then you can figure out the amount of change in temperature, which is what I'm showing with the vertical axis here, the change in temperature from the different effects of these pollutants that end up in the Arctic region. And those effects are highly diverse and are the result of co-emissions of these different pollutants. So this is a kind of very actually tricky accounting problem as well as a modeling problem. So you have activities like black carbon on snow. So black carbon, when it deposits on snow, changes the reflectivity of the snow, the albedo of the snow, which then results in net warming, essentially net warming everywhere. Then you have direct atmosphere effects of black carbon. So this is the darkening the atmosphere and making the atmosphere itself a little more absorbent. Cloud effects are really hard. Then you have direct and indirect impacts of organic carbon and sulfate and ozone. Methane is really important in this picture because methane emissions are a precursor for tropospheric ozone. So methane itself is a warming pollutant, but tropospheric ozone is also a very strong warming pollutant. The NOx effects are tricky to model. So you've got to get both of these right if you're going to do the accounting properly. Here's what's interesting to me. First of all, you have big warming effects from all the sources you expect, and you have some big cooling effects from these co-emitted species. The other thing that's very interesting to me is I've put a red line here between the countries that are official members of the Arctic Council and the countries that aren't official members of the Arctic Council, but whose emissions have a large impact in the Arctic. And in particular, East and Southeast Asia, the rest of the world to some degree, and the rest of Europe. But the big story is it's right here. And so this is worrisome because it means some of the original hypothesis around working in small groups with existing institutions, that hypothesis is not going to hold. And so we need to know something about the identities of the countries and the incentives of the countries who might not be official members of the Arctic Council, but whose behavior could be pivotal, at least in the generic sense of the word pivotal, and actually maybe in the technical sense of the word pivotal to cooperation in the Arctic region. So that's what we're going to try to unpack over the next few slides. So that gives you some sense of what the source-receptor relationships are for each of the different pollutants. And then we need to know something about the concentration impact relationships for each of those. So how are we going to do this? Ideally, you'd want to do this by integrating the analysis into the Sand et al. Kind of model. So you had full transport and chemistry of the entire Arctic region. That's computationally very, very difficult, and those models don't have sufficient resolution on their emissions to be able to actually do the analysis that we need to do, which is a country level resolution. We want to know the costs and the benefits at an individual country level. So we're going to use the second best strategy, which I think right now is the second best, and there's still some more work to be done to understand whether and how that second best strategy is in fact a very good second best. We're going to use the TM5 model. So this is an atmospheric chemistry with physical transport model, but we're going to use a variant of this that is just now emerging, and one of our co-authors is the key person on that, which is a reduced form version of this that operates at 56 regions in the world. So it sacrifices resolution in the atmosphere for the benefit of resolution at the country level, which is exactly what we need if we're political scientists, because we care a lot about what happens in individual countries and the benefits and costs those individual countries see. So that's how we're going to make the trade-off here between computational intensity. We're going to focus it in on getting the country level resolution. So let me put a chart here that shows you. So this gives you a sense. This is maybe Europe's vision of North America, which is a car in Mexico causing pollution in Russia. That's actually, the Mexican car industry is not a big source of pollution in Russia, but this is our image. Maybe this is a post-Trump image of what's going on in North America. But in case you've got this car, and the emissions coming out of the car are going to affect things that people care about in other countries, in addition to things that people care about in Mexico and the Caribbean. So they're going to care about impacts on human health, impacts on crops. They're going to care about impacts on climate. There are other potential impacts, but we believe the analysis is dominated by this. We've done some work to try and defend that assumption. So let me just walk you through the elements of doing the analysis behind each of these potential kinds of impacts. For crops, analysis of crop impacts is relatively straightforward because you estimate the impact in terms of lost productivity of the crops. You look at the value of those crops as they're traded in global markets, and that's a good first approximation. In the full-blown version, you'd want to do this in equilibrium so that you understand the macroeconomic effects of the change in the crop prices and so on. We haven't done that, but please don't get angry at me about that because it turns out the crop impacts are just irrelevant to the overall picture. This is dominated by human health and by climate. To look at the impacts on human health, we need to know something about the relationship between different concentrations of tropospheric ozone and particulate matter, fine particulate matter. We're working in PM2.5, fine particulate matter on human health. That, fortuitously, the World Health Organization has done a lot of work on. So we can figure out the impact on lost years of life, and then we need to know something about the value of those lost years of life. And so we're going to do something that's fairly standard in the literature and gets everybody angry, so be ready to be angry, but it's standard. And that is, we're going to tell you something about the value of a life, the value of a statistical life. So we're going to use the OECD methodology, which is focused on the average value of an average person in Europe in 2005 dollars, $3.6 million. And so if you're upset that your number should be higher or lower, or whatever it is, just deal with it for now. We'll talk more about this later. We've done a lot of work to change the valuations here and there and look at sensitivity of this. It's not going to change the fundamental results here. It changes some of the details. But that tells you something about the value of a European. That tells you something about the statistical value using this method of a European life at European income levels. The value of life, of course, changes as people get wealthier or if they're poorer. Because as a general rule, people who are much wealthier place a higher value, and that value is not a simple one-to-one relationship. There's an elasticity between the two, and so we're using fairly standard methods to try and get a sense at the value of human lives in different parts of the world. This table just summarizes what we're doing for different income levels, all indexed to 2010, with different kinds of elasticities, meaning the relationship between income and the change in the value of statistical life. That is fairly standard methodology. That, I can say from the IPCC experience, was extremely controversial. And actually, I think half of the writing team for one of the chapters 2 assessments ago resigned because of the controversies around whether you could use this method, which is widely used in economics for thinking about converting everything into dollars, as to whether that was legal, whether that was ethical, and so on. So this is a very, very controversial issue, and I expect we're going to get a lot of hate mail about it, but it's not really the dominant concern here. We're going to calculate damages using the social cost of carbon. Why do we even do this? We do this because a lot of people have spent a lot of time trying to figure out how you monetize the damage caused by climate change. And using the methodologies around social cost of carbon, we're going to use the median values that came out of the Obama White House, They've now disappeared as a matter of federal policy, but federal policy can't erase the science that's been done behind it, so we're going to continue to use these numbers. And we have the advantage that the Nordhaus, the one variant of the Nordhaus-Dice model, which is a widely used model in the economics of climate change, allows us to disaggregate the overall social cost of carbon, which is dominated by the global impacts of climate change, down to individual national levels. And we care about that because we ultimately want everything to be in dollars and everything to be at the individual national level, so we can think about national costs and benefits. So I want to show you over the next few slides, which is where I'm going to end my talk. I want to show you over the next few slides. Once you've gone through these 3 steps, here's what you get in terms of results and the intuition behind those results and what it means for policymakers, and I think also for the entire field of political science. First, we're going to try and calculate the benefits and costs to countries, to themselves, as well as to other countries in the region for these 2 different pollutants. And you're going to learn a lot from this table, because what we're doing here in this table is for soot on the left side. We're going to look at the overall benefits from controlling soot pollution, which is the main warming ingredient in soot is black carbon, and methane over here. The atmospheric lifetime of soot is several days to a week or so. So this is a very, very short-lived pollutant. And soot has large impacts on human health and on crops, in addition to on the climate. As a political scientist, soot is a beautiful pollutant, because even for countries that don't care anything about climate change, it kills lots of people. And so it creates an incentive to do something about the underlying problem, because you're worried about the impact on human health, and then fortuitously along the way you have an impact on climate change. And I know that sounds like a very kind of crass, hard-nosed way of thinking about the world, but one of the ways to move from broad aspirations like let's all hug each other and stop global warming at 1.5 degrees to here's a serious plan by which countries can actually control emissions and stop warming at various different levels. The way you move from the broad aspirations to actual real plans is thinking about what are the incentives for countries and for firms and so on to actually go off and act. So this is just the benefit side of the equation. What's interesting to me is if you look at the benefits from controlling soot to yourself, and on the top here are members of the Arctic Council, down here are members that are countries that aren't in the Arctic Council but are observer states. You look at the benefits to yourself versus the benefits to other countries in the region. The benefits for soot, essentially everywhere, except in the Nordic countries, essentially everywhere are mainly a story about self-benefits. And that kind of intuition behind that now makes some sense, because soot has a large impact on human health and so on. Whereas methane, the story is exactly the opposite. By the way, these ratios over here are a ratio of benefits to yourself versus benefits to other 6 countries. It's not a cost-benefit ratio. This is giving you a sense of the intuition behind whether countries, by controlling the pollutant themselves, are going to benefit themselves, or whether the story around benefits is for the collective benefits to other countries. So that's very, very important.
Just clarify what the unit on mitigation is, KT?
Yeah, so these are mitigation levels, thousands of tons of mitigation against this is called a policy scenario. So this is a scenario that UNEP and WMO have developed where they look out to the year 2030 and they adopt maximum technically feasible measures. So it's actually a crazy policy scenario, because nobody in the real world actually adopts maximum. Well, there are actually some parts of American environmental law that are written this way, but even when you look at how it's implemented, it's never implemented this way. So nobody actually does this, but it's a convenient test to stress a model like this to see what happens if you go to what's maximally feasible. Now, this is only about the benefit side of the equation, and if you've been in the first week of economics, you say, well, what about the cost side of the equation? So that's what I want to now focus in on more in the cost side of the equation. And we'll say that in terms of the benefits, we can understand something about the relationship between different countries in the region. So what I'm going to show you here are the 2 largest dyads for all the Arctically relevant countries, and the fraction of benefits that they're exporting, if you like, by emission controls, the fraction of benefits that they're exporting to other countries in the region. So these are not all the dyadic relationships, because that produces a spaghetti diagram that nobody can see straight around, but these are the largest 2 dyadic relationships for each of the countries. And these are, we're looking at benefits from climate, that's avoided climate change, calculated using the social cost of carbon, and non-climate benefits is improvements in crops and human health. Essentially all of this is a human health story. And what you see is Russia is a huge exporter. If Russia were to control its emissions, the benefits would actually flow more to China than to the rest of Western Europe. China and India are gigantic co-polluters of each other. And so they have a joint interest in doing something about their pollution, and I'll quantify what some of those interests are in just a second. So I believe last two quantitative slides, and I'm going to conclude here. First exercise I want to go through is, now that we know something about the benefits, and we know whether the benefits accrue to the country that's controlling emissions itself versus to other countries in the region, we need to know something about the costs as well. And so to get that cost information, we use the database and the Monte Carlo analysis that I showed you earlier that kind of, I'd say, overstates the certainty with which we really understand the costs and efficacy, but it is a good place to start. And I'm going to walk through the cost-benefit calculation in two steps. First, I'm going to say, compared to the business as usual emissions, the emissions that you think would happen without a big change in policy, if countries just knew their own interests and equalized marginal costs and marginal benefits, what could they do just thinking about their own self-interest? What could they do to control emissions? So the back bars in these charts here show projected levels of emissions out in the year 2030 from no big changes in policy, the standard business as usual scenario. The middle bars here show emissions. These vertical axes somehow dropped off. Is again in 1,000 tons in the top from soot, 1 million tons for methane in the bottom. And what you see going from the back bars to the middle bars is just by thinking about self-interest alone. If countries were just run by a czar who had taken no class other than basic resource economics and could implement whatever was socially optimum for the country, you'd see a huge reduction in soot. And we have some sense of how to quantify that now, and also to quantify the impacts of the climate. And then what's in the front bars is, suppose countries thought about their interests collectively. How much additional reduction in emissions would happen as a result of moving from complete autarky, self-interest, and only self-interest thinking about no other country, to thinking about collective interest. And so if there's a big difference between the middle and the front bars, that tells you as an international relations scholar, we need to be thinking about international cooperation because we want to get those extra benefits from cooperation. And what you see for the case of soot is there's almost no difference. Our uncertainty analysis shows there's also almost no difference. So the soot story is almost entirely a story about countries learning more about the health and mainly health impacts of soot, and then through self-interest alone doing more to control their emissions. And you can imagine a lot of scenarios whereby countries wouldn't think about their own interests properly, and there'd be market failures and so on, and you could add that to a model like this, and that's a great additional research project and so on. But the idea here is to just do the first analysis and see what the numbers look like. Methane, the story is very different. Self-interest alone, especially large countries, can have a significant interest in reducing their emissions of methane because more of the benefits of controlling that methane are appropriated inside the country itself. But to get to the socially efficient reductions in methane requires significant cooperation between countries. Self-interest alone doesn't get you there. Why do you care about this? You care about this because when you take a step back and look at the actual policy debates in the world, almost all the actual policy debates in the Arctic region around these pollutants are inside the Arctic Council, focused on the core members of the Arctic Council, and focused on soot. And what we found is that that is completely wrong. That the game here is not about soot. Soot is an education problem, if you like, but the real cooperation game is around methane, and the real cooperation game is about the biggest emitters of methane, who, even though they're not in the Arctic region, a fraction of their emissions end up in the Arctic region, and a small fraction of the big number is still a big number, and that's China and India. So 2 weeks ago, we briefed the Norwegian delegation to the Arctic Council, which, along with the Finns, are now chairing the Arctic Council and driving the agenda here. And they were actually, ironically, on their way to the next Arctic Council meeting. And we said, here's what we found. Everything you're doing is not right. It's not so welcome. But what we have been working with them on now is a strategy to work with the Chinese and the Indians to create a different club that is under the umbrella of the Arctic Council, but a club that's oriented around China, India, Russia, and the United States. And those are the countries that generate most of the benefits in there. Ironically enough, it's actually the United States that appears to be the hardest nut to crack right now, but that is not a permanent feature of American politics that may change in 1,110 days or whatever we are. Not that anybody's counting. And so that's a really important policy insight from work like this. We've started to look at all possible combinations of clubs. So clubs that are small, like 2 countries, up to clubs that are as large as they could be given the analysis we've done, which is 7 countries. We're treating the Nordic countries as a single country for data reasons. And so what you see here for methane and for soot is in soot, as you go from a club size of up to 2, which is the minimum size club, 2 countries getting together and cooperating, as you go up to clubs above size 2, essentially 100% of the potential benefits from cooperation are realized by the club. And that's a reflection of the story that the soot story is almost entirely a self-interest story. Whereas methane, small clubs, if you choose the right members, can get you 30 or 40% of the potential benefits from international cooperation. But you cannot get close to the maximum benefits unless you have club sizes that are up in the range of 5 or 6. And even if you look at club sizes that are 5, if you're really dumb about organizing your club with 5 members, you can end up with a club that performs very, very poorly. This chart here in the middle just shows you those results, but for the 2 short-lived climate pollutants, soot and methane together. I'll draw your attention to this red dot right here and to the orange right there. The orange is the median performance of all the potential clubs that have club size 4. Red is the performance of the formal members of the Arctic Council. So if the Arctic Council continues to operate as it is, the maximum benefit the Arctic Council can produce if countries think reasonably rationally about their situation is only 40% of the potential for reducing these pollutants in the region. Whereas if the Arctic Council just throwing darts at a board, if you like, not quite darts, just throwing darts at a board with other kinds of clubs, the Arctic Council could do much better. That's the kind of policy application that we're deriving from this, which is fundamentally political science work. It's work at the core of a rationalist view of political science and international political economy. The countries think about their interests, and they cooperate, and they build institutions, try and help them to cooperate. And I want to just close with a few key points, which is we now have the capacity to calculate essentially all the elements needed to do political science, or international relations, international political economy studies of the costs and benefits by country, which is what matters, in the Arctic region. And there's no reason to think that that can't be done in other regions, because essentially all the same models could be repurposed for that. It allows us to say something about the policy configurations and offer some policy advice. I've given you some sense of where we think the frontier of the policy advice is right now. And frankly, the advice we're giving to the countries that suffer a lot from lack of additional pollution control, but have themselves directly no capacity to control the problem. And I want to say where we're really headed is just lay out an agenda and now tools that'll be available off the shelf so that people who are at the frontier of political science, who are interested, hopefully, in changing policy debates, but also interested in changing the way political scientists think about the work that they do, how they can do the political economy analysis. We've done it now at the country level. The logical next step is to work at the sectoral level to do a domestic politics, political economy kind of analysis. There's an obvious question for side payments. We're now in the process of calculating potential side payments. And I think this is what science should be, is you lay out a kind of framework for doing things, and then it also lays out an agenda for what you do next. And I think we're now at that point. So let me stop there, and I look forward to the discussion. And I don't know how early you are or what the rules are, but maybe just raise your hand.
So I kind of warned you about this one, but that was great, really interesting, but it still assumes that nations would act even in their own national self-interest. And it assumes that they can control industries. That is, that politicians and agencies are not manipulated by the very fossil fuel industries, especially, right, that are driving these problems of short-lived pollutants.
Right, so this is precisely why we're doing why we carry the sectoral level information, even though I'm not using it for the analysis here. Here's why. We can, from many of the standard indicators of government quality and corruption and so on, the comparative politics people use all the time, we could develop a little algorithm that would tell us something about the extent to which a country thinks about the public interest, versus the extent to which they think about private, well-organized private interests.
Wait, who's they? Is that the decision makers?
Decision makers of the country. So that's, first of all, that's frankly all the work on resource rents is in some sense about the same idea. So one could imagine developing a little algorithm that would tell you whether the country's going to think about public goods or private goods. That's the first thing. Second thing is we could develop an algorithm that allows us to weight certain sectors more heavily than others. And so I think that's what one wants to do next. The reason we didn't do that first is because for all the criticisms that people levy against simple, national, cost-benefit, kind of rational calculations, they are where our discipline starts. And they are also, I think, where any serious analysis like this should start, because the intuition you get from that, just in the beginning, the intuition you get from that is the two problems. Even though these are all short-lived pollutants, and even though the whole literature has been treating the short-lived pollutants as in the same bucket as, gee whiz, isn't there a stronger interest to do something about the short-lived pollutants? What we've been able to demonstrate now quantitatively is that that's wrong, is that even these two short-lived pollutants are actually very, very different in their underlying political properties. So I think that's where to go.
Yeah, thanks for a great talk. That was all of you.
I'll let you go ahead.
Sorry. Still thanks for my question, excuse me, is a little bit about the competing interests within a country, right? So you've assigned a weight to, say, the soot problem, right? But if you look at China, right, their goal is not to generate soot. Their goal is to electrify and to industrialize and do all these other things. And so while they're trying to deal with the soot problem as quickly as possible, they're trying to do it in a way that balances against all these other things. And so as in your analysis, it doesn't seem to be that those other things as competing interests. And I'm just wondering how you think about that as you present what a country's self-interest is.
Yeah, so we've done it in the most stylized way here. And I think we can go another round or two in terms of adding more resolution inside the country. And at that point, this framework stops being useful. I think we can go in the Timmons direction of unpacking the domestic politics by sector, unpacking the extent to which governments are kind of captive agents of rentier portions of the economy versus public goods providers and so on. My read of the comparative politics literature is at that point, this kind of framework stops actually being helpful for the analysis. And then you need to start doing richer descriptions inside the country. I will say that for all of the beating up on the Chinese, and others of you are actual experts in China, but let me offer an opinion and hopefully not let too many wrong facts get in the way. The Chinese are doing a tremendous amount. And it's nothing to do with climate. It's all to do with exactly what you said. Concerns about local air pollution, political protest around that. There's now a lot of tangible evidence that the impact on GDP is significant. So even if you didn't care about people wanting to throw you out of office, just the GDP effects would be important. And so, actually, I think to some degree the Chinese are behaving this way. The more interesting case for me is India, because in the Indian case you have a clear overall income levels are lower, and so the value of statistical life is lower, and so the cost-benefit calculation runs out in a different way. But still, the Indians are not delivering on what you would think of as a normal calculation of self-interest. And I think that's because of a massive administrative feasibility problem. And so that, I think we can, in my response to Timmons, you could imagine putting some of that into the model here, but I think I'd be shocked if we generated a lot of new insight from that. I think we have to work inside the country and look at it. So actually a lot of people doing that right now. And so I think the story, at least on the surface, is easy to understand. Fixing the problem is hard.
So I wonder if your framework can contribute to questions of how cost-benefit analysis is used in politics. So the Obama administration got into a lot of controversy for using global measures of benefits for evaluating social cost of carbon and other mitigation strategies, in contrast to the OMB policies and norms that only domestic benefits should be looked at. A lot of people argued that this was manipulating the standard protocols that the Obama administration wanted to do this. They should just say it, but they shouldn't pretend that it's consistent with the way OMB has evaluated regulations in the past. Is there a way to escape any of that politicization?
No, there isn't. Yeah, so let me say that we are reporting an SI, but not on the main paper. Was the paper circulated in advance? Looks most like it was not circulated in advance. But I'm happy to send anybody a copy of it. If you want to see the draft, it's a constantly evolving activity. But The main paper we're reporting full social cost of carbon analysis, 2/3 to 3/4 of which is exactly as you say, global effect, not national effect. That's always struck us as not quite right for exactly, not for the administrative law reasons, but because you really want to calculate just self-interest. And so we're reporting an SI now, an SCC, a social cost of carbon calculation, where it's just the self-benefits. It's hard to disentangle that because of the way that we do the disentangling with the DICE model, but that's probably a more accurate description of the actual appropriable climate benefits from a country thinking entirely about its own self-interest. When you work it all out, the impact of all that on the Soot story is still small, because Soot's basically a you're killing your own people story, except in Norway where you're suffering, like 2 Norwegians die because of the rest of the planet, but they're unhappy Norwegians. And that's an exaggeration, that was a joke lately there, 2 Norwegians, headlines, Yankee Norway. The methane story might change. The intuition behind the uncertainty analysis that we've seen, where we take all the values and put them to extreme low, extreme high, which is how we're doing the indicative uncertainty analysis. I don't have the slide with me. What happens is that the optimal club size moves around a little bit, from 2 or 3 countries up to 5, maybe 6. But the shape, to me what's interesting is the shape of the line doesn't change. I wish I had that slide with me. The shape of this line doesn't change. It flattens a little bit, and depending on where the uncertainty is, the benefits of working in small groups are larger or smaller, but the overall intuition doesn't change very much. Yes, you're exactly right. It's interesting because this is like a Rorschach test. So there's tremendous bipartisan support for cost-benefit analysis, going back to 12-291, the executive order in the Reagan administration that set up cost-benefit analysis in the U.S. government. And then the question really is, how far do you take it? I think we may well see under the current administration effort to roll back even 12-291. That would be extraordinary. I can't really see it happening, but there's a lot of things I haven't seen happening as a political scientist in the last year. But I share the sentiment that what the Obama administration did was a standard deviation or 2 outside what would be a reasonable interpretation of country-focused cost-benefit analysis.
Yeah, I was trying to follow the logic of the whole presentation. At the beginning, I understood why you would want to focus on a specific region, and that made a lot of sense to me. But at a certain point, when you were calculating the flows of benefits, then it suddenly became quite global.
Right.
And I lost track of how that was related to the impacts or the costs and benefits of behaviors specifically for the Arctic region.
Yeah, so this is a very important point. So our motivation in doing this is to focus in a region where the source-receptor relationships would be relatively tight because of the zonal partial isolation of the Arctic region. But when you do the calculation, the cost-benefit calculation, and you're thinking about how could a real country use this? A real country would never do the calculation only from an Arctic point of view. So we're doing the calculations from a global cost and benefits point of view, but we're focusing the analysis on the region where those benefits might be concentrated because of the geography. And so this is in part because we think that's the way real countries behave, and in part because our larger interest here is to understand to what degree could motivation from being in a region where the benefits of emissions control might be relatively concentrated, to what degree could that spill over into broader cooperation. So the next step for people who study international cooperation with this work, there's actually one group in Norway, not part of our writing team, but close friends and collaborators, who are building agent-based models that allow us to simulate at the country level what individual countries do in cooperation. And so one of the things we want to do now is we can parameterize some of this, put this into an agent-based model where you initiate the model with an Arctic club, and then you see to what degree the benefits of cooperation spill over to other countries, and then you can have cooperation evolve from there. But no, that's a very astute comment.
So that seemed to be to some extent to undercut the value of having started with that focus on the Nordic region, and particularly because in the end, the Nordic Council seems not to be the key thing. It's China and India, which are, they're relevant, of course, but the institutional apparatus that you said it's so important to have it in place because then you can do things.
Right.
But actually, we don't have China and India in place to do things. So I just lost the
Right, so,
thread.
but I think that is actually, our priors going into this were that there would be enough appropriable benefits in the Arctic region that the Arctic Council itself could justify going off and doing something. We believe that so strongly going into this, maybe that's because half the writing is Norwegian. It's just wrong. And so that's a problem, because it tells us that even in the region where the existing institutions are already doing a whole bunch of stuff and are motivated to do more about the problem, we can't even, in fact, we also report in SI just the Arctic benefits. We cannot justify on a cost-benefit calculation those countries working hard on the problem. And so that's why the advice finally that we offered, you know, we're one scientific team and we're getting lots of other people telling them what to do, the advice we offered was the Arctic Council, and keep talking to the Arctic Council and so on, but if you really want to have an impact on the problem, you've got to do something with these other countries. I will say, as a footnote to that, that's not completely alien to what, for example, the Norwegian government has done in other areas. Norway is the architect of a very effective, it appears to be very effective fund to help promote reductions of deforestation in the tropics, for which Brazil was the first recipient of significant money, now Indonesia. And so there are other areas where they have seeded clubs that are in their self-interest. And so what we're arguing that they do is seed a club like that in China and India.
So I actually we need to cut off the time. We're out of time here, but we have a reception upstairs, which you're all invited to, where we could continue the conversation. But let's thank David Becker.